invalid address being pushed in by mistake. You also have to worry about function inlining, because on these platforms, having such little RAM and such little stack space, it's more efficient to inline a function and save that call on the stack, even if you have enough flash memory to hold it. Because the code executes from flash memory, it does not execute from RAM. And in simulating these, you might want to dump out things to show you how your application is running, or whether it's working. Or if you're trying to take something apart, you'll want to poke its different I/O addresses, or fuzz it virtually, rather than in hardware. So I'll be showing you an example of a Stack Overflow in simulation. This is on a von Neumann chip in which RAM is executable. So it's the easier type to overflow. To exploit a Harvard chip, you have to actually call existing code, or rather the tails of existing code, to move your attack from RAM into flash memory. It becomes rather involved. So here I did a nice little simulation to beamer dump, and I can single step through it. So as main begins, it's going to call load, which has no exploit, no exploit occurs here, and then load over, which it does. And each of those will call string copy. So as I advance, you see the program counter goes to 1170, which is the load function. Then the load function grows the stack as it enters. It then calls string copy. String copy begins writing, and you'll see Cafe Babe be written to the stack. And it stops copying when it has a null. This is just a standard Stack Overflow exploit that ends on a null. And then that function returns, and for load to return, it's going to pop the stored value in main, that's 11E0, into the program counter. And it does this, and then main calls load over, and you can see load over begin writing everything with Fs until it's told to stop. And then it will overwrite the return pointer with 210. Now the return pointer has been overwritten, and as the stack rewinds, it's going to jump into RAM instead of the place that it came from in main. And this is how you perform foreign code execution on a microcontroller. And with wireless sensor networks, you can do this because they're on a network. And you can speak on that network as soon as you compromise one of them. And you can fuzz these things. You can do it either being omniscient or blind. So in some cases, you might want to rip the code out of a microcontroller without knowing what's already there. To do this, you start injecting fragments that might reset the chip. And you keep doing it until you can make it return into the bootloader. You know it's in the bootloader because it's masked ROM. It's the same on every chip. So when I was attacking one of these with Aurélien Francien, we started sending random packets. And the random packets would have just repeated fields of the entry point of the bootloader. And then we just waited for the bootloader to start up and say hello. We could tell this because a certain I/O pin would become an input pin. Whenever we failed, it would just reset and we could get another try. And on the few cases where it locked up, we just hit the reset button. And this worked very quickly. And then once we had that foothold where we were in the bootloader but we didn't have administrative access to the bootloader, then we could change our exploit code. Then we could make it elevate our privileges before it returned. And we found a blind way to actually use the code that was already in flash memory to pop a value into register 11, which controlled the access privileges. So we set up our exploit to run existing code within flash, not knowing where it was. And since we already knew the field offset, we could just guess at the address that we would return to. And sure enough, 20% of the time, it falls exactly where we want before it locks up. So we can hit the reset button a couple of times, and in 3 or 4 seconds, we have access to the device. You can detect a reset of the chip because all of the I/O pins become high-impedance inputs. If you have an output pin and you put two large resistors across it, one going to VCC and one going to ground, the output will ignore those two voltages. But if you have an input pin, then the value will be the fraction of those two by the difference in the voltage. So if you've got a 100 ohm and a 300 ohm, then the voltage might be 1/4 of the high voltage. And this is easy to measure, this is easy to detect, so you can tell when you've caused the chip to crash and reset. So you can fuzz it to create a crash, and then having found the crash, you can adjust your offset until you get execution of code that you know to already be within the device. And then you begin trying to execute foreign code. So in the case of von Neumann chips, you can just return straight to RAM. Okay. In the case of Harvard chips, Aurelian wrote a neat little paper on using return-oriented programming for microcontrollers, in which he was actually able to use enough of the existing code in a wireless sensor to move an exploit from RAM into flash memory so that it could be executed. And he did all of this movement without being able to run any of his attack code. This is at CCS in 2008. It's well worth looking up. And then together we just published a paper at the Usenix workshop on offensive technologies that describes how to do the blind return-oriented programming, calling code in flash memory, just guessing that it will be there by the ways in which compilers arrange things. So in our case, the compiler would open every function with push R11, push R10, push R9, push R8 to save the values in those registers before changing them. And then it would end with the opposite sequence. Pop R7, pop R8, pop R9, pop R10, pop R11, return. And the credentials to the master ROM bootloader were stored in register 11, which means that the fragment of code we wanted, pop R11 return, was actually the most common sequence of 4 bytes in all of flash memory. So it was very easy to find that location by guessing. I've been doing some work on a neighborly Tennessee belt buckle. You might have seen a Shmoocon, which actually is a wireless sensor, and it runs around by broadcasting random strings. And then when it receives a string, it puts it into a small buffer, and then it replays it, along with a random reply. So if you have two of these together, they just start bouncing back and forth, and they display the packet on their LEDs, and they blink, and you can say, hey, I've got a belt buckle too, and everything is grand. If you're in the field in the middle of nowhere, it'll just sit there silently and occasionally broadcast a short thing to look for another belt buckle. But if you have one of these in the presence of a regular Zigbee network, it starts broadcasting random packets with valid checksums that are part of the MAC protocol, just in response to anything that it hears. So it starts fuzzing everything around it. I won't actually be releasing this, but I've only had one person come up and tell me while I was planning to release this, you know you will kill someone, right? Because medical equipment runs on this. You have pulse oximeters that you can clip onto the finger with no external power supply that will send patient data to a computer without having a tangled nest of wires. You have fly-by-wireless in aircraft. The electric grid is running on this technology now to signal changes between electric meters. So I've covered all of these things, and I've had to skip over a few exploits that I might have otherwise presented in more detail. And I've got plenty of hardware to play with. So after this lecture, I'll be going to the hardware hacking village in the BSD tent. And if you'd like, we can play with my equipment, and I can actually walk you through some of the exploits of wireless sensors. Or we can stick an oscilloscope into one to spy on the traffic that's occurring within it. I've also got packet sniffers for ITC and SPI, so you can watch commands run from the microcontroller of the